Okay, hi everyone. My name is Shane Chen. I'm a graduate student at Yale. Today I'll talk about a new approach to probe primordial non-Gaussianity by reconstructing the initial conditions with machine learning. Sorry, this. Okay, so gravity also induced nonlinearities, and that's a source of confusion when we try to measure primordial non-Gaussianity. And by reconstructing the initial conditions, we can remove this gravity-induced nonlinearity, and that can strengthen our signal from primordial. So we want to go from this late-time nonlinear density field back to the initial linear density field. The traditional algorithm, which is based on perturbation theory, gets us here, which is less nonlinear, but quite far away from an initial condition. So I use a hybrid reconstruction method that combines the CNN and the traditional algorithm. And so that gets us here, and that's much closer to the initial condition. So in terms of cross-correlation coefficient with the initial conditions, so we can see that this hybrid method performs significantly better. And so I train a model with simulations without PNG and then apply that model to simulations with PNG. And that still works very well. So here are simulations with PNG that have local type of FNL plus 100 and minus 100. And so we have a reconstructed density field, and then we can go to constrain primordial non-Gaussianity. So let's take a look at the information at the field level. So here I expand the reconstructed density perturbatively up to second order. So this is the first order delta delta G, and the other three terms are the usual quadratic terms. And this delta FNL, that's the new term that we introduced, which is defined as phi G squared. M phi has the transfer function. So in simulations, I have an initial condition. So I use the no PNG initial condition for delta G, and also use that to compute the gross shift tidal terms. And so we have all of these terms, and then we can do a least square fit to find FNL. So in matter density field in 1 gigaparsec volume in real space at ratio of 0 for FNL, for simulations with FNL plus 100 and minus 100, we can get a constraint about plus minus 92 with an error about 5. So the fits are slightly biased, but the error is much smaller. And so compared to pre-reconstruction, we can get about 2 times improvement in error. So that's in 1 gigaparsec volume. So for surveys that have more than 2 gigaparsec volumes, for example, DESI, we can expect even smaller error. So that's approaching our sensitivity goal of measurement error less than 1. Okay, so this hybrid reconstruction method shows promising constraining power for primordial non-Gaussianity. So it's significantly reduced gravity-induced nonlinearities, and at the same time preserves most of the primordial non-Gaussianity information, and that gives tighter constraints. So that's a very powerful approach to constrain PNG with larger structure surveys. Thank you.